Tonight, the solar system holds its breath. A mysterious visitor from deep space designated 3I Atlas is hurtling through our cosmic backyard. It's the third interstellar object we've ever confirmed, and it's about to make an incredibly close pass by Mars, just 0.19 astronomical units away. Every probe, every orbiter, every sensor we have around the red planet is being pushed to its absolute limit, racing to capture every last bit of data from this fleeting encounter. But this isn't just another space rock. 3I Atlas is breaking all the rules. It's shrouded in a blazing emerald green coma, a color that has astronomers baffled. It exhibits strange, erratic microaccelerations, tiny nudges in its path that defy our understanding of cometary physics. And its chemical signature is rich in carbon dioxide, a composition that's virtually unheard of for objects of its kind. It has shattered every page in the comet playbook. The stakes are about to get even higher. In just a few hours, Earth's own instruments will go blind. Our planet's position relative to the Sun and Mars means we lose our direct line of sight to the object. It's not a technical glitch, it's a cosmic alignment. For 6 critical hours, a handful of Martian probes will be our only eyes and ears. They will stand as the sole witnesses between humanity and the truth. So what is 3I Atlas? Is it just a bizarre 1 in a billion natural comet? A cosmic oddity that will rewrite our textbooks? Or is it something more? Something engineered? Something that could redefine our very definition of what it means to be alien? As the countdown to the flyby ticks to 0, the clues we gather signs of fragmentation, unnatural energy pulses, strange spectral signatures could change everything we think we know about visitors from the stars. Will these next few hours reveal an extraordinary truth, or will they simply prove that science, with all its rigor, still holds the final word? The clock is ticking. We have a 6-hour window before our view of 3I Atlas vanishes behind the sun. 6 hours. At a distance of about 28 million kilometers from Mars, the interstellar visitor will race past the red planet just as our terrestrial observatories are plunged into a communications blackout. This isn't a failure of planning. It's a consequence of orbital mechanics, of celestial geometry. For this brief, tense span of time, Mars becomes the single most important observation post in the entire solar system. Every major asset in Martian orbit, NASA's MAVEN, the European Space Agency's Mars Express, and the ExoMars Trace Gas Orbiter is shifting into high-cadence observation mode. Their teams are running pre-scripted drills, but they're also ready to improvise on the fly. This is an unprecedented event, and everyone knows it. Inside the MAVEN Control Center, a specialized team known as the Red Watch Crew is taking the lead. These are the operators trained for high-stakes contingencies, the ones who run complex decision-making models for every conceivable anomaly. In the hours leading up to the blackout, they've been rehearsing everything: rapid switches between standard science instruments, and burst-mode spectroscopy, ready to pivot in an instant if a sudden flare or a debris alert flashes across their screens. Backup configurations are loaded. Redundant cross-checks are being run with the teams at TGO and Mars Express. Every single command is logged, and every data packet is duplicated. When the rest of the solar system is blind, there is absolutely no room for a single point of failure. The observation schedule is merciless. Mars Express will be snapping wide-field images every few minutes, stacking its exposures to catch even the faintest hint of fragmentation or an unexpected course change. At the same time, TGO's advanced spectrometers will sweep the object's coma, hunting for spectral lines that just don't belong, for chemical fingerprints that defy a natural explanation. AVEN's particle sensors and magnetometers are on high alert, monitoring for any ripples in Mars's ionosphere, anything that might hint at an unnatural interaction between the object and the planet's thin atmosphere. Each spacecraft's power and telemetry budgets are stretched to their absolute limits. Observation slots have been negotiated down to the second. There's a contingency plan for everything. If a sudden burst of debris from 3I Atlas threatens the orbiters, Mars Express is programmed to immediately switch into a safe observe mode, sacrificing precious data to ensure its own survival. The abort threshold for this maneuver is razor thin, set just 30% above the last measured density spike from the object's coma. This 6-hour blackout isn't just a communications gap. It's a full-blown stress test of our entire interplanetary science apparatus. The Red Watch Coalition is acting as the central nervous system, relaying commands and data through narrow intermittent relay windows, constantly prioritizing instrument health, and coordinating with surface assets like the Perseverance rover in China's Zhejiang. In control rooms across the globe, clocks are counting down in parallel, synchronized to the comet's final approach. And it's not just the big space agencies. Outside, a global network of amateur astronomy arrays is listening intently, waiting for the first sign of a photometric spike, ready to upload their own data to a global alert network the moment they detect anything unusual. For these 6 hours, the fate of this entire observation, and potentially the answer to whether 3I Atlas is a cosmic oddity or something deliberately engineered, rests on the flawless performance of a handful of robotic orbiters and their dedicated teams millions of miles away. The urgency is real. The tension is palpable, and the margin for error is razor thin. The universe rarely gives us opportunities like this, and we have one shot to get it right. Let's break down the potential clues these orbiters are looking for. First, fragmentation. Comets are fragile. If 3I Atlas is a natural object, the intense gravitational pull of Mars could cause it to break apart. Observing how it fragments, or if it fragments at all, can tell us a lot about its internal structure and composition. A clean, uniform break might suggest a natural, icy body. But if it shatters in an unusual pattern, or resists fragmentation entirely despite the stress, that would be another mark in the unexplained column. Second, those unnatural pulses. Ground-based radio telescopes have already picked up faint, sporadic bursts of energy coming from the object's vicinity. Are these just natural plasma interactions or something more? The close-range sensors on MAVEN and TGO are perfectly positioned to determine the source. We're talking about a potential technological signature, a hello from the stars. Third, spectral oddities. The emerald green coma is already a huge mystery. Green in comets usually comes from diatomic carbon, which is destroyed by sunlight within a day or two. For 3I Atlas to maintain such a vibrant green halo suggests it's producing this chemical at an incredible, and perhaps unnatural rate. The spectrometers on the Mars orbiters will perform a detailed chemical analysis. They're looking for isotopes that don't match our solar systems, or complex organic molecules that hint at something beyond simple chemistry. Finding unexpected heavy elements or non-natural isotopic ratios would be a smoking gun for an artificial origin. Each of these data points, fragmentation, pulses, and spectra forms a piece of a larger puzzle. Separately, they might be dismissed as anomalies, but together, they could build a case that is impossible to ignore. This is why the coordinated effort is so critical. Mars Express provides the visual context, TGO gives us the chemical breakdown, and MAVEN measures the object's interaction with the space environment around it. It's a multi-layered investigation happening at 100,000 kilometers per hour. As the first data packets begin to trickle back through the deep space network after the blackout, scientists will be in a frantic race against time to analyze them. The initial findings will likely be cryptic, filled with jargon and raw numbers. But hidden within that data could be the answer. We might find that 3I Atlas is simply the weirdest comet we've ever seen, a natural wonder that forces us to expand our models of the universe. It would be a phenomenal discovery in its own right, proving that the cosmos is far more diverse and surprising than we ever imagined. But what if the data points in the other direction? What if the fragments move in controlled formations? What if the pulses resolve into a clear, repeating signal? What if the spectrum reveals alloys and elements that can only be produced by advanced technology? If that happens, then tonight will be remembered as the night humanity confirmed it is not alone. The night a visitor from another star system rewrote our place in the universe. The wait is almost over. The probes are in position. The teams are ready. The solar system is holding its breath. Whatever the answer is, the next few hours will undoubtedly change our perspective on the cosmos forever. Have you ever looked up at the night sky and wondered if we're truly alone? Well, a recent discovery might just make you wonder a little harder. Meet 3I Atlas, a celestial object that's rewriting the rulebook on comets. As it gets closer, every second feels like a turning point, with a trail of unexplained signals leaving astronomers baffled. It all started with a backyard telescope in Pune, India. A citizen astronomer named Priya Ralo noticed something strange. A repeating pulse in the object's light, brightening and fading with a rhythm that no textbook could explain. Her discovery went viral, and soon, the world's most powerful telescopes turned their gaze towards 3I Atlas, and that's when things got really weird. Photometric records confirmed the object's brightness was surging at incredibly regular intervals. These pulses, spaced by nearly identical gaps, were nothing like the random flares we see from typical comets. Each spike had a sharp onset and a clean decay, almost as if someone or something was flipping a switch. Even as it neared the sun, this perfect rhythm held steady, unaffected by distance or solar glare. But the light show was just the beginning. When scientists analyzed its chemical makeup, they got another shock. Instead of the usual water vapor, the dominant signature was carbon dioxide. The CO2 to water ratio was a staggering 8:1. A chemical fingerprint so rare our current models can't even replicate it. And then there's the color. The cloud of gas surrounding the object, its coma, glows a brilliant emerald green. This isn't just a faint tint. It's an intense, stable hue confirmed by telescopes both on the ground and in orbit. The usual chemical reactions that make comets green just don't explain this level of intensity. Adding to the mystery, the object is unusually rich in nickel, far more than any other comet we've ever observed. Images of its dust tail add another layer to this puzzle. The dust grains are larger and slower than normal, drifting in a wide, lazy arc. It's as if they were released in measured bursts, not the chaotic jets we expect from a melting ice ball. Perhaps the most mind-bending discovery comes from tracking its movement. Astronomers have detected tiny accelerations, micro-course corrections that don't match any known outgassing pattern. And here's the kicker. Each of these tiny nudges perfectly coincides with a pulse of light, suggesting a direct link between the object's light and its motion. No single one of these anomalies would be enough to cause a stir. But when you put them all together, the rhythmic pulses, the bizarre chemistry, the intense green glow, and the strange movements, you get a portrait of an object that defies every category we have. The evidence is piling up, and scientists are scrambling to find a single explanation that can tie all these incredible facts together. So, what could it be? The first and most grounded hypothesis takes us to the coldest, most distant reaches of our solar system. The idea is that 3I Atlas was born in a region so frigid that its chemistry was fundamentally altered. In this deep cold, carbon dioxide could have frozen into a dense, crystalline structure, trapping other gases inside like a molecular cage. As 3I Atlas journeyed towards our sun for the first time, the increasing warmth would cause this superdense CO2 ice to sublimate, or turn directly into gas in a very controlled, explosive way. This process, known as a solid-state greenhouse effect, could explain the regular, pulse-like bursts of light and the controlled release of dust. The unusual chemical ratios, like the high nickel content, might be explained if the object formed in a unique pocket of the primordial solar nebula. This exotic ice theory is elegant because it uses known physics and chemistry to explain many of the object's strange behaviors. It paints a picture of 3I Atlas not as an alien messenger, but as a pristine relic from the dawn of our solar system, carrying secrets from a time and place we've never been able to study up close. It's a compelling idea, but it's just one of several possibilities being fiercely debated in the scientific community. The truth about 3IDL ACE is still out there, waiting to be discovered. This comet was formed far from any star, in a place so cold that water freezes solid, and other ices, like carbon dioxide and carbon monoxide, are far more common. Comets from the distant Oort cloud often show this kind of chemistry. But what makes this one so strange is its carbon dioxide to water ratio. It's an incredible 8:1. We've never seen anything like it. Still, the counter-argument is that space is vast and our catalog of comets is tiny. A single outlier could completely rewrite what we thought we knew about cometary chemistry. A second model looks at the comet's structure. Imagine deep pockets of volatile gases trapped inside, like cosmic champagne bottles. As sunlight slowly warms the comet's crust, these pockets could erupt violently. If these pockets are spread out unevenly, it could explain the rhythmic pulses of brightness we're seeing. Lab simulations have shown that even small temperature changes can trigger these sudden jets. And if the layers inside are stratified, these eruptions could repeat with a certain regularity. It's rare, but after billions of years of cosmic weathering, it's not impossible. A third explanation focuses on the dust. The comet's emerald green glow and the presence of large, slow-moving dust grains might be due to an unusual dust composition or size distribution. As the comet nears Mars, The solar wind and the planet's weak magnetic field could be shaping the tail, herding charged grains of dust into those broad arcs we've observed. Models of comet tails show that under certain conditions, heavier grains lag behind, drifting in lazy curves that look a lot like the measured bursts. The comet's light also shows a negative polarization, which is more typical of rocky asteroids than icy comets. This could hint that the grains are compact and rich in carbon, not just fluffy ice. Finally, some scientists are pointing to the limits of our own models. We've only ever studied 2 other interstellar visitors up close. Every new arrival like this one pushes our simulations to their absolute limit. The tiny accelerations and synchronized pulses we seeing might just reflect physics that our software cut and yet capture subtle interactions between sunlight, gas release, and the comet's tumbling motion. From this perspective, the anomalies aren't evidence of something exotic, but a humble reminder of how much we still have to learn. For every puzzle, the scientific community demands that we exhaust every natural explanation first. For these critical 6 hours, Mars becomes the only observatory in the solar system with a front-row seat. 3 orbiters, MAVEN, Mars Express, and the ExoMars Trace Gas Orbiter form the backbone of our investigation. Each one is equipped with a unique set of instruments, tasked with capturing a different piece of the puzzle as the comet passes. MAVEN's imaging ultraviolet spectrograph is scanning the skies tuned for faint emissions. It's looking for ultraviolet traces in the comet's tail, searching for any signs of it breaking apart or having sudden outbursts. Its particle counters and magnetometers are running at full tilt, watching for any ripples in Mars's ionosphere. A sudden spike in charged particles or a twist in the magnetic field could signal that something more than natural chemistry is at play. If the comet's dust or plasma interacts with the Martian atmosphere, MAVEN's sensors will be the first to know. Meanwhile, Mars Express is focused on direct imaging with its visual monitoring camera. It's taking long exposure shots to track the comet's coma, hunting for any evidence that the core is splitting or changing shape. Its spectrometer is scanning from ultraviolet to infrared, looking for any spectral lines that don't belong, unexpected emissions, or even a surprising lack of water vapor. Its plasma analyzer is also monitoring for energetic ions, which could betray a non-standard interaction with the Martian environment. Finally, the ExoMars Trace Gas Orbiter, or TGO, is using its spectrometers to probe the coma for trace gases. It tests hunting for isotopic ratios or molecular fingerprints that are different from anything we've seen in our own solar system. Its high-resolution imager is trying to catch any fragmentation events or dust jets in the act. All this data is being logged with precise timing, cross-referenced in real time between the teams on Earth. Their environmental sensors and cameras act as a crucial backup, providing a ground-level perspective to complement the powerful orbiters high above. Are there weird spectral or radiation signals that science can't explain? Do the isotopes look different from what we see in our own solar system? Only when different instruments and different perspectives all point to the same conclusion can we even begin to think we've found something truly unprecedented. This protects the precious data from solar interference, transmission errors, even corruption during the long journey through space. Mission teams have a system to fast-track the most interesting data packets, the ones flagged for possible fragmentation, strange energy readings, or sudden changes in trajectory. Every potential event has to be double-checked by at least 2 different instruments, and the raw data is then posted to public archives for everyone to see as soon as possible. The chain of custody isn't just for numbers. It's for physical samples too. If an orbiter's collector actually catches a dust grain or an ice fragment, a special group of planetary protection officers takes over. The very first public alert of a spike in light might actually come from one of these citizen scientists. But even then, professional teams immediately triage these uploads. As the data flows in from Mars, this matrix will define the final verdict on 3I Atlas. The conservative path is the most likely. It assumes every anomaly can be explained by rare, but natural comet behavior pockets of gas erupting, dust grains with unusual chemistry, or a series of micro-collisions. This is the default, the scientific baseline. Messaging plans have been drafted in advance for every possible scenario, stressing transparency without sensationalism. Who decides if it's just a rock or something more? Decades, the SETI post-detection policy was the only guide, a quiet agreement among scientists on how to handle a confirmed signal from an extraterrestrial intelligence. What about a visitor? Tangible object that flies right through our cosmic neighborhood? The flyby of Muenwe in 2017 and Borisov in 2019 forced a major rethink. This isn't just another scientific document. Playbook for one of the most profound moments in human history. Think of it like a traffic light system for the unknown. A nominal classification means the object is behaving like a normal comet or asteroid, even if its path is unusual. It might have a strange shape or a unique chemical signature, but its movements are predictable, governed by gravity and the sun's heat. We study them, we learn from them, and science marches on. Focus becomes data triage, quickly downloading the most critical information before a potential catastrophe, one everyone secretly hopes for and dreads at the same time. Extraordinary. This classification is reserved for anomalies so significant, so strange, that they challenge our fundamental understanding of physics and chemistry. To trigger an extraordinary classification, you need more than just one weird signal. If, at the exact same time, our instruments measure tiny, inexplicable accelerations, as if something is pushing the object, then we have a match. Two separate, bizarre phenomena, happening in perfect sync. Or what if two different teams, using two different instruments, both detect spectral lines in the object's coma that don't match any known chemical element or compound? That's the kind of converging evidence required. No single signal, no matter how tantalizing, can open the door to what the protocol cautiously calls engineered possibilities. Every scientist, every operator knows the stakes. This isn't about jumping to conclusions. It's about a rigorous, evidence-based process for confronting the truly unknown. This new framework isn't just about classifying objects. It's about a radical commitment to transparency. The days of scientists hoarding data for months or even years are over. The new protocols demand that every single byte of data from an interstellar flyby gets uploaded for public access within hours of being received. NASA, the European Space Agency, and Japan's JAXA have all agreed to create mirrored archives. As soon as a ground station confirms the data from a spacecraft is clean, it flows to open servers accessible to anyone. Automated computer programs constantly scan this incoming data, flagging any outliers for immediate review by experts. This means that a strange signal can be identified, verified, and shared with the global community in near real time. It's a complete paradigm shift. And it's not just the professionals who are involved. This new era of interstellar monitoring embraces the power of citizen science. Around the world, a registered network of amateur astronomers, from observatories in Pune, India to backyard telescopes in Patagonia, are now part of the first line of defense. They upload their own observations of brightness and position directly into vetted data pipelines. This system ensures that the first alert of something unusual can come from anywhere, at any time. A crucial discovery made in a backyard could trigger official scrutiny from major space agencies within minutes. This global collaboration maximizes our chances of catching every detail, ensuring that no clue, no matter how small, gets missed. The story of the fictional Comet 3I Atlas is a perfect illustration of why these protocols are so vital. On October 3, 2025, as this interstellar visitor passed within about 18 million miles of Mars, the new playbook was put to the test. Every major piece of hardware at the Red Planet, from NASA Maven orbiter to Europe's Mars Express and the ExoMars Tracegas orbiter, stopped what it was doing and turned its full attention to this celestial traveler. Rovers on the surface pointed their cameras to the sky. For over 40 hours, they collected an unprecedented stream of high-cadence data, a flood of information relayed back to Earth. The signals were unlike anything ever seen from a comet before. It had a strange emerald-green glow. It pulsed, brightening and dimming with a steady rhythm. And its spectrum showed it was venting huge amounts of carbon dioxide. As per the new protocols, all of this raw data was released for open analysis almost immediately, becoming part of the public record for anyone to scrutinize. Scientists around the world jumped on it. They found that while natural models could explain some of its behavior, like the CO2 emissions, key anomalies remained. The pattern of tiny, unexplained microaccelerations and the perfectly synchronized pulses of light still have no definitive, natural cause. The extraordinary classification hasn't been triggered because the evidence isn't conclusive enough. Was there engineered activity involved? We still don't have the answers. What is certain is that the 3I Atlas encounter has forever changed how we prepare for visitors from deep space. It field-tested our new protocols, proving that a rapid, transparent, and global response is possible. It showed the power of combining professional and amateur observations, and it set a new, higher standard for data sharing and collaboration. The reforms put in place aren't just for the next interstellar object. They are for every future messenger from beyond our sun. They are designed to build transparency, trust, and a global playbook for the unknown. Whatever 3i Atlas ultimately proves to be a natural curiosity or something more, its flyby of Mars has fundamentally altered how we watch the skies and how we prepare to talk about what we might find. The universe is speaking, and for the first time we have a plan to truly listen. Thanks for watching. If you're fascinated by the mysteries of space, be sure to subscribe and hit that notification bell so you don't miss our next deep dive into the cosmos. See you next time.